The COVID-19 pandemic presented a major issue. How could we quickly test individuals to determine if they were infected? One solution was the COVID rapid antigen test, which is cheap to manufacture and easy to interpret, making it well suited for mass distribution and use in low resource settings. This test is an example of a lateral flow immunoassay, or LFA, a versatile paper-based diagnostic that detects a target analyte by producing a visible readout of 1 or 2 lines. The LFA test line intensity varies depending on the amount of analyte in the sample. However, the LFA suffers from 2 major limitations.
First, the visual output of the LFA makes it inaccessible to the blind or visually impaired user, which is significant as nearly 7.6 million Americans suffer from a visual disability, rendering the LFA inaccessible to a large portion of the population. This issue especially affects those living in medically underserved communities, which are disproportionately affected by this visual impairment. Second, since the output of the LFA is the intensity of a single color, the LFA has a limited quantitative resolution, making it difficult for use in highly sensitive applications such as therapeutic drug monitoring or TDM, where small differences in dosage can have toxic effects.
Our team qLFAID from UCLA. To address LFA inaccessibility and the lack of quantitative readout, our team created the Quantitative Lateral Flow Assay Interpretation Device, or qLFAID. The qLFAID is able to analyze any commercial LFA using a neural network that we trained with over 2,500 images. We designed our device with several accessibility features, including tactile and auditory cues that will guide a blind or visually impaired user throughout operation.
For the qLFAID's accessibility, we conducted a blindfolded demonstration. The individual is first prompted to insert the LFA into the device. Afterwards, the individual presses the start button in Boston Braille to begin analysis. Once the results are ready, the vibration module and speaker alert the user to press the start button to receive the results. The final prompts then ask the individual for next steps. The entire procedure takes around 2 minutes and is very accessible for blind and visually impaired users.
Tested this device on a sample TDM LFA we developed, we found that the device was highly accurate when evaluating analyte concentrations. For concentrations across the clinically relevant range, the average predicted concentration for each condition using our image analysis algorithm is shown on the right, with true sample concentration on the x-axis and predicted concentration on the y-axis. Overall, we were able to successfully correlate the intensity of each test line to the concentration of analyte in the sample using the qLFAID.
Finally, the qLFAID is also very affordable. The cost to produce the prototype was around $140, but the cost anticipated to be significantly cheaper when produced commercially. Due to its reusable nature, the qLFAID only requires an initial one-time cost and a relatively inexpensive replacement LFA cartridge for each test. Thus, even at the current price point, the cost to operate the qLFAID is much cheaper than the ELISA test, the current gold standard for TDM. Moving forward, we would like to test our device in commercial LFAs and receive feedback from blind and visually impaired people. We hope this device will fulfill an unmet need in healthcare, and thank you for listening to our presentation.